In this video, we are going to discuss static single assignment, which means a register should be assigned n minus once inside a program. So we already discussed a little bit details about this in a previous video, but in this video, we are going to go a little bit deeper and discuss its details and its properties and why its motivation basically. So static single assignment is usually pronounced as SSA. So what is SSA? It is, as I said, the rule that a register should be defined n minus once inside the code. So here, for example, let's say this is a program and $bar is a register, and say this is defined here as 482, and later it is again defined as 777. But this is not allowed because $var is defined twice in this program. So this is categorically rejected by the type checker, which says that, oh, this register is defined twice, and as a result, it doesn't satisfy SSA, and so we are rejecting this program as a valid input. So in more general, this $var equals blah blah should appear n minus once inside the entire program or in the entire function body. But for your information, it is different from memory locations onto which value can be stored multiple times. For example, you can store 482 to a memory location A, and later you can store another value, for example 37, to the same location inside the same program. It is perfectly valid program because SSA doesn't require anything about the memory locations. SSA is fundamentally about registers. Maybe later we can discuss memory SSA, which is SSA for memory locations, but it is a little bit more advanced topic, and we are not going to discuss for the time being. So for now, let's assume SSA is fundamentally associated with registers, not memory locations. And then now the question is this is basically the definition of SSA. What is SSA? And we need to ask ourselves another question, which is why SSA? Why we are discussing static single assignment and why we introduce SSA in our compiler implementation. The primary reason is that it makes much easier to implement optimizations because this property, which is called the SSA property, is the analysis of the optimizations and compilers, because it is guaranteed that there's no interference on the register that is just being defined. If $var is defined 482, then it is guaranteed that there are no other instructions that assign other values to the same register, which is basically an interference on the analysis. And as a result, $var should be 482 for the rest of the execution. So it is guaranteed that there's no interference on the value of this register. So the value of this $var should be 482 from now on, period. So it makes the life of optimizations much easier. If you see an instruction that says $var equals to 42, then you can just replace every occurrences of every read of this $var by 42, because there's no interferences and $var should be 42 in the execution. So this is true, and as a result, we can implement constant propagation very easily. This property not only eases the implementation of constant propagation, but also those of other optimizations as well. So we are going to discuss the other optimizations in a later video of this lecture. Okay, so that's the reason why SSA is generally preferred in the compiler implementation, and that's the reason why in the KECC, our compiler, we use SSA in IR. And yeah, so one step further, KCC's IR, in KCC's IR, even register names are canonically named like this. So we use %x, %y, and variables in the examples, but in the implementation of this KCC, actually, all register names are canonically named like this. %b37 colon I42, which means that it is the register that is being defined at the 37th block, 42nd instruction. So this is block ID, this is instruction ID. So these two numbers completely decides where this register is defined. And as a result, we can make sure that statically make sure that this register is defined n-most once. And yeah, this is by construction, KECC's IR satisfies SSA. And the IR gen, which produces an IR from C, is guaranteed that it produces a valid SSA IR. And the reason is that, recall from the previous lectures that each C expression is translated into IR instructions, and as a result of the translation of an expression, you're going to get a register. It may be a constant, but in general, you are going to get an IR register. So you're going to create a new IR registers for each expression. So you're not going to reuse the existing register. That's the reason why we are not going to need to define a register twice. So you're going to just create new registers, that's all. And if it is difficult to do so, we just create local variables in the memory. So we are going to create memory locations which is not subject to this SSA, which can be stored multiple times. And if it is strictly necessary in the translation, we're just going to use it. We are not trying to make it a register in the IR gen because it complicates the algorithm. We just use memory locations if it is easier to do so. For example, we call that such an expression, such a conditional expression, which is assigning the value of B or C depending on the value of A to T. So here we avoid, in a naive translation, it may be possible that you first calculate A, and depending on the value of A, you jump to the next blocks. It can be either the true block or the false block. And in the true block, you're going to calculate this B, and then assign the value of this B to register. And in the false branch, you're going to calculate the value of C, and then write this value to the same register. But the problem is that it doesn't satisfy SSA because these two blocks, the block for this true branch and the block for this false branch, both write to the same register. So the register, let's say this is %t, is defined multiple times in the code, in the true branch and the else branch. So it is defined at least twice. So it breaks the SSA's property. So we cannot do such a translation. So in order to circumvent this problem, we are going to use local variable in the memory. So at the beginning of the translation, we create a local variable that will store the intermediate result of this translation. And in the true branch, you are going to just store the value B to the memory location. In the else branch, you are going to store the C to the same memory location. It is perfectly okay because memory locations can be stored multiple times, whereas the register should be defined only once. And later in the join block, in the continuation block, we are going to just load from the memory location and use it as the result of, use it to store to this memory location T. So this is basically the translation strategy we discussed in the previous lecture. And as a result, we could preserve, we could satisfy the SSA property in the IRGen's output. So, okay, this example, the key message of this example is that IRGen never produces an invalid SSA program. It only produces a valid SSA IR program. Furthermore, in a later stage of compilation, the pass or optimization that is called mem2res is going to convert memory locations into registers, but it is guaranteed that it produces only the code that satisfy SSAs. So it introduces registers and it defines many registers in the translation, but it guarantees that all the registers are still defined in most ones. So this is basically the key SSA construction algorithm that is used in the KAIST. So mem2res is basically creating an SSA registers, and these SSA registers are exploited in other optimizations. For example, as we saw in the previous slide, the constant propagation algorithms will exploit the fact that this ampersand var should be 42 in the rest of the execution. We are going to discuss other kinds of optimizations as well. For example, the global value numbering or other optimizations, dead code eliminations also. So this SSA is extensively used in KCC, as we discussed. It is baked in the KCC's IR, and IRGen guarantees that only SSA program is generated, and optimizations are going to recognize SSA registers and exploit the properties. Now let's turn to the a little bit deeper technically. So now we can raise a question. So okay, it is very good to define registers only once, but maybe it is impossible for loops. Let's see this example here. So in this example, we are going to define a local variable I. Let's say it is meant to be a register instead of memories, because you're going to represent this program in SSA registers. So it is initially 0, and in this while loop, it is checked whether this I is less than 10, and if so, it is incremented and go back to the loop pad. You can see that in this C program, the I is redefined. It is initially defined here, but redefined inside the loop body. And now the question is, or the problem is, how to express this idea, which is very widespreadly used and which is perfectly valid code in C, that the I is changed, the value of I is changed inside this loop. So how to express this idea in SSA? It is perfectly valid question. It is important question for the usability of SSA, because such an idea should be representable in the registers in order to compile this code efficiently. But at first glance, it looks like impossible because I is actively redefined in this loop, and we cannot avoid the redefinition here. And it breaks, it looks like it fundamentally breaks the properties of SSA, which says a variable should be defined only once. But people found a solution to this problem. So people found that if we introduce special kinds of registers, that is called finals, then we can express this idea using SSA registers. So here's an example. So this C program is translated into this SSA program using a fine node here. So let me explain this code a little bit. At the beginning of the execution, you're going to just assign 0 to a register, which is as it is ampersand I0. That means it is a register for I, but there are many registers for I, so we are going to name it just I0. And in the second block, it is going to jump to the second block as in the C program, the control flow goes from this line to this line. And we're going to define I1, which is assigned I0 or I2, depending on from which the control flow went. So if the control flow went from this to this, then the I1's value should be I0 here. And if the control flow went from this block to this block, then the value of this I1 should be I2. So phi node has such a semantics. Depending on the previous block, it can be either I0 or I2. So in the beginning of the execution, the control flow went from the initial block here to this block. And as a result, I1 should be this I0. So this is 0 at the beginning of the execution here. It matches with the C program given here. I is initially 0, and in the first iteration of this loop, I should be 0. And the condition is calculated, and depending on the condition, we jump to either this next block or the end block. If this condition is true, then we are going to go to the loop body here, which is calculating I plus 1, basically. Because I is assigned with I plus 1 here, so we first need to calculate I plus 1. And when we go back from this block to this block, which is matching with the C program where the control flow goes from the end of the loop to the head of the loop, the I1's value, which is meant to be the value of I at the time of this iteration, is going to be I2, which is I2 here, defined here as I1 plus 1. So yeah, using these phi node registers, which gets assigned the values depending on the previous block, we could express this idea here. At the beginning of the iteration, I should be the initial value here. And otherwise, this is incremented, and this incremented value or the last value is assigned to the value at the loop head, I1. And using these special kinds of registers, we can see that all registers are defined at most once. I0 is defined here, I2 is defined here, I1 is defined here. Maybe in the iteration, this I1 could be defined multiple times in runtime, because we can visit this block multiple times. But statically, this I1 should be defined once. So that's the reason why we say it is static single assignment, not dynamic single assignment. Statically, all variables statically all registers are assigned at most once. So that's the meaning of this SSA. This SSA property will be discussed a little bit deeper when we are going to study the optimization algorithms. For example, the MEM2RES and the GBN or CONSPROP. And especially when we study the MEM2RES algorithm that converts memory locations into registers, we are basically actively trying to insert phi nodes instead of memory locations. So in when discussing the optimization, we are going to study this kind of final registers further. So let's now, in this lecture, let's assume it is useful in a later stage of compilation, and let's study just the definition of these SSA registers and finals. So in KCC, we are going to represent these SSA registers using what is called block arguments or extended basic blocks. So in this representation, jump is associated with arguments. So we are going to jump to the block 7, but previously we just used only we just annotate this jump with B7, for example, the block ID. But in addition, we are going to annotate the jump with values, the list of values. This is basically arguments for the block. When you jump to the B7, you're going to provide 2 arguments to the block, which is A and 42. And conversely, each block is associated with parameters, which is meant to be equivalent to the final registers. For example, let's declare that B7 has 2 registers, or 2 parameters, or 2 final registers, which are called X and Y. And the interesting thing is that when you jumped using this jump instruction to B7, then the value of these X and Y are getting assigned with A and 42 because they are arguments and they are parameters, and the parameters are bind to the arguments given to the jump register. So you can think of it as a function call. You are going to jump to the B7 or calling a function like with arguments, and the callee will have 2 parameters which will get assigned with the caller's arguments. So in KCC, these registers parameters are canonically named as like this. So this means that B7's zeroth final register, and this is block 7th first final register. So this X and Y, such a useful name, may be annotated with the registers, but canonically it is named like B7 column P0. So this is similar to the naming scheme for the instructions like this. This is, for example, B37's instruction 42, which is defined at the 42nd line in the block. And similarly, we have B7's final, zeroth finals or nth final, which is the nth finals defined in this block. Okay, here's an example. Here is a final. Let's say that a block 7 has 2 finals. X gets the value of A or B depending on the predecessor or previous block. So if the control flows from the left predecessor to this block, then X is getting A and Y is getting C. And if the control flows from the right predecessor to this block, then X gets B and Y gets D. So in this block argument representation of SSA or extended basic block representation of SSA, it is represented like this. In the left predecessor, we are not going to just jump to the B7. We are also describing which values are given to as an argument to this block. Here, this is A and C, because this A will be the value of X and the C will be the value of Y when the control flows from the left predecessor to this block. On the other hand, in the right predecessor, the jump instruction is changed from just jump B7 to jump B7 with arguments B and D, because the value of this X and Y gets B and D when the control flows from the right predecessor to this block. Okay, this is basically how we are going to represent the finals and SSA registers inside this KAIST. So please memorize this form because you're going to see what's going on in the IR, and you need to manipulate this IR on your own. So please memorize this form, and please memorize how to represent these finals in the KAIST. Most importantly, please memorize what is the SSA and what is the motivation of SSA, and how to represent such a loop variable in SSA using finals. Okay, so far we discussed how to represent SSA registers inside this KAIST, and of course there are many remaining questions. We only discussed the what and a brief why of SSAs, and we're going to study further topics on SSA. For example, how not to break SSA basically when you convert memory locations into registers in mem-to-reg optimization. So it is fundamentally related to SSA construction algorithm, which is inserting finals to make sure a program satisfies SSA. So we are going to discuss this algorithm in a later part of this course. And on the other hand, we are going to answer this question: how to exploit the SSA properties, which means that if a variable is assigned with a value, then variable should be the same with the value in the rest of the execution because there is no interferences. So how to exploit these SSA properties in optimizations concurrently. So we have a vague feeling that this kind of information will be very helpful in optimizations. But we need to concretely discuss how to exploit this kind of information in the optimization of the IR. So for example, constprop and global value numbering or other optimizations use SSA properties, and we are going to discuss how. So this video was about the SSA registers, and it will be extensively used in the IR part of the course, IR and optimization part of the course. So please use this video as a starting point to study SSA. And if you have any questions, please ask questions in the issue tracker, or just search for the SSA in the Wikipedia or other online sources and see what's going on there. And if you are really interested in this topic, so please, I refer you to the original paper of SSA, which I'm going to post in the issue tracker. Actually, this SSA is my favorite concept in the program languages study. I mean, I believe SSA is the single most important idea in the last 30 years of study of program languages. I mean, it not only enables us to implement efficient optimizations easily, but also it greatly helps improving the performance of, for example, setting analyzers or model checkers or other kinds of program code analysis tools. So this is fundamentally related to efficient representation of programs, which is one of the main topics of this course. So if you have to learn only one concept from this course, I would like you to study this concept of SSA more extensively. So I strongly recommend you to study this.